How's everyone doing today? Tired, nervous. I would say that's a reasonable percentage of me too. Tired and nervous. Not necessarily because of a test coming up, but yeah, hangry. Go get some food and watch the live stream. Oh man, coffee. Well, I don't like coffee so much, but I have tea right here. So, any tea lovers out there? Let's see. Awesome. Glad there's some tea lovers here. It's not all about coffee. All right. So let's take a look at the second version of this practice exam. So I put a little bit more emphasis on the later material. But again, I made do with the time that I had. So let's get started. So, on this version, there is going to be similar questions on this to the last version, but I've changed largely pretty much everything in some form, asking for plenty of different things, but all related. Now, any general questions before we get started? This is available to download on the Canvas in the same location as last time, so... And the plan for tomorrow will be to go over one final version in person. So the time is going to be 1 o'clock tomorrow in the room listed on Canvas. So refer to the Canvas announcement for the rest of the information, but 1 p.m. tomorrow afternoon, right before the test. I'll see if I can bring a little candy for you all. Throw out a couple of types of candy that you prefer, and I might bring some of it. So I'll reward people who participate. Also, I'll talk a little bit more about this later, but I'm currently working on something on my website which will allow you to interact with the practice exam and actually, select a multiple choice basically on my website. So I'm going to work on that tonight, and I'll send out an announcement tomorrow if I do anything with it, but it'll be a way of letting you gauge on your own if you're ready for the real exam. So, but for now, let's go over this. Skittles. Skittles are really good. Snickers. Okay. Twix. All right, let's see what I can do about that. I'll keep that all in mind. Skittles is definitely going to be in that mix, personally. First question. So we have monochromatic orangish light with wavelength given, 600 nanometers, shines onto the two slits, and a pattern is observed on the wall. The light going from each of the two slits takes a different path to the same location along the wall, and hence two different path lengths. So in the figure, if it wasn't quite clear, you can see here's the two slits in the diagram, and there's two different routes that the light can take to the same location from the two slits, which means that one of these paths has to be longer than the other path, unless it's the center. And the center means it's symmetrical and the path length is no different. If a bright fringe is observed on the wall, which of the following could be possible differences between the path lengths? So in other words, how much longer is one of the paths compared to the other? list all answers. So there can be more than one answer here, possibly. So you have all these different answers, and they all seem to have a relatively common factor in them, which is either 150 or 300. 150 could go into pretty much all of these, but also 300 will go into some of these other ones. You'll also kind of notice that the wavelength of the light is 600 nanometers as well, so it does have something to do with that. So the thing to remember conceptually about how these bright and dark fringes form on the viewing screen has to do with constructive or destructive interference. So what you want to remember is that for constructive interference, so for this problem, constructive interference implies that two waves will perfectly line up with each other, so crest with crest and trough with trough. So you would have, for instance, one wave here. This could be the wave from path 1, and there could be a second wave, for instance, from path 2, which lines up perfectly with it. And that means that there is either no difference at all, so the difference would be 0, or you could take the bottom wave or the top wave and shift it over by one entire wavelength. Because what you'll see here is if you take, for instance, the peak of this red wave that I've drawn and you shift it over one wavelength, which is going to map exactly to where the next peak is, it's perfectly identical, so it will just line itself back up if it's one whole wavelength. And you can do that for any whole number of wavelengths. So in other words, the shift is m lambda, and m is equal to 0, 1, 2, 3, and etc. So I could have no shift, m0, or I can have any of these whole number of wavelengths that I can shift it over and it will still line up. It will still be constructive, or in our case, it will be a bright spot. The destructive will have that the two waves will look opposite to each other. So one of the waves on the bottom will look like this, and the other one will be just the mirrored version of it. And how you get a mirrored version is by shifting it by half a wavelength instead of a full wavelength. So for these, the shift is basically m plus a half lambda. And this looks familiar because it's part of your formulas, which says that it's either m lambda or m plus a half lambda for the constructive and destructive. So this one says that for if m equals 0, 1, 2, 3, etc., m equals 0 means you get a half out of this, so you get half a wavelength. So half a wavelength makes it destructive, and you can do any number of these, which will end up resulting in a whole number of wavelengths plus an extra half, always. So that extra half a wavelength is crucial to make it destructive and hence a dark spot. So with that kind of, information that you want to recall, take this problem, for example, where you have the double slit. And in this double slit problem, you know that you're observing a bright spot that I'm telling you about. So I don't really care so much about the measurements in here and the little details, but I do say that the two paths that light takes to reach a particular spot on this viewing screen ends up being a bright spot. And bright means that it's constructive. So bright implies constructive, which therefore means that you must have a shift of m lambda. Okay, so m has to be a whole number, so you can have 0 wavelengths, 1 wavelength, 2 wavelengths, 3 wavelengths. So if, let's say, if our wavelength is, in our problem, 600 nanometers, with that wavelength, we can multiply that by any whole number, and we can get exactly what's going to be constructive. So in our case, we would have that for m equals 0, 1, and let's say we do up to 2, we will have that the shift will either be equal to 0, 600, or 1200 nanometers. So these would be three possibilities in terms of your path difference. So if we look at our options here, you'll notice that I have 0, 150 is not one of those, 300 is also not one of those. You have a 600, 900 is not, and you have a 1200. So there are actually three correct answers here. 0 nanometers, 600 nanometers, and 1200 nanometers. So path 1 or 2 can be longer by any of these three amounts, 0, 600, or 1200, and you will get a bright spot. It just so happens that if you have 0, then that means both paths are the same length, which actually results in the center bright spot. But now if you were to rephrase the question to the dark spot, what you would be looking for would be everything in between the 0, 600, and 1200, meaning you would look for 300 and 900 instead. But again, in this problem, it's 0, 600, and 1200. So A, D, and F. So the answers are A, D, and F. All right. Let me know if you have any questions on anything relating to superposition or how you do this kind of double slit problem where you're not typically using the double slit equation that you're used to using. So. Does the color of your light matter? Well, the color is related to the wavelength. Now, if you want a more, I guess, accurate picture, of the relation between color and these numerical numbers that you're using, technically, we associate color with the frequency of the light, not the wavelength. It just so happens that we can relate the frequency to the wavelength, and then we can match up a wavelength to a frequency. But when you do other things like talk about light refracting and other effects that happen to it, you're supposed to pay attention to the frequency that's associated with the color. But beyond that, let's say that we can associate a wavelength with a specific color. If you change the color, then you're going to get a different wavelength. And in this case, according to this, the path length difference between the two has to be some whole number times your wavelength in order to get a bright spot. So whatever your wavelength is, you're going to multiply that by a whole number, and that will definitely affect your answer. So let's say if you change your wavelength to 400, then that means your answers will be 0, 400, 800, 1200, and etc. So the wavelength matters for the question, not the color itself. Yeah, to I guess be a little bit more precise with the wording of the question, yeah, it didn't really matter that I told you it was orangish. It just so happens that 600 nanometers is orangish. No problem. Okay, number 2. You have monochromatic light with a wavelength of 600 nanometers shining through 2 slits, which are separated by a distance of 500 micrometers and projected onto a wall which is 100 centimeters away or 1 meter. What angle from the center, so just like everything else we're measuring from the center, what angle from the center of the pattern is the first dark fringe? Okay, so this is more of a typical double slit problem that you will solve. So what we're going to do for this is we're going to use the d sine theta equals m lambda. So here we go. We have the same general setup here. I'm just going to talk about a dark spot instead. So we know that from the center here, okay, so our line of symmetry in the problem, we have bright spot in the center, m equals 0, and then another bright spot, 1, 2, and then symmetrical. Okay, so the dark spots in between the bright spots is what we're going to care more about in this case. So this one is essentially equivalent to 1/2. The next one is essentially equivalent to 3/2, so let me actually write it as a decimal, so 0.5 and 1.5. Okay. So those will be your effective M values for that. Now we want the first dark fringe from the center, which means it's going to be this one right here, which I've labeled as M effective being 0.5. So there's a viewing angle, theta, from the center axis. We're going to find that angle in this problem. So we're going to say that d sine theta equals either, again, you can either write m lambda, but you need to use a number that has a half integer in it, such as 0.5 or 1.5. So for dark, you could use 0.5, 1.5, 2.5, etc. Or if you don't want to do that and you're more comfortable doing this, d sine theta equals m. Is it written as plus or minus in this version of the formula? It's written with a minus. M minus a half lambda. Okay, so in this version of the formula, all you care about is that the stuff in the parenthesis lines up with your numbers here. So this stuff in parenthesis needs to be either 0.5, 1.5, 2.5. So in other words, in this formula, you would just plug in an m value, subtract off a half so that you would get 0.5. So in our case, so since we want the effective m value to be 0.5 for the first dark fringe, we're going to say that we want the whole thing to be 0.5, which means therefore that you would plug in m equal to 1, so that 1 minus a half is 0.5. Okay. So again, we'll only care about that stuff in the parentheses and what the total value ends up being, regardless of how the formula is written. Now, regardless of how you choose to approach this, we want to solve for theta. So we're going to solve it for theta. We need to divide by d. So we have that sine theta equals, I'm going to stick with the top formula for the simplicity and just plug in 0.5. So m lambda over d. And you can take the sine inverse of this to solve for the angle. So therefore, theta is the sine inverse of that side, which is m lambda over d. And we can drop in the numbers. So we have sine inverse of m effective being 0.5 for a dark spot, the first one. The wavelength being 600 times 10 to the minus 9th meters. And the distance between our two slits being given as 50 micrometers. So 50, 10 to the minus 6th meters. So we're going to plug all of this in. And for that, we get 50, 10 minus 6th. Bottom, multiply across 0.5, 600, 10 to the minus 9th. And take the sine inverse of that. And you get 0.34 for that. So out of our answer choices here, we have 0.34 is the first answer. So the answer to this one is A. So is A. All right. So this is a little bit more closer to what we're used to doing. So This ends the double slit questions, so let me know if you have any other questions on double slits, and then we'll move on to the next topic. Now, you mentioned Twix earlier. The real question is left Twix or right Twix? Describe in words what each of the variables stand for. D is the distance between the two slits. Theta is the angle to whatever spot you're looking at on the viewing screen with respect to the center. So again, in this diagram here, it's this angle right here between the center and whatever spot you're looking at. And then M is the order number. It's essentially counting the bright or the dark spots, but you have to remember exactly what you're supposed to be counting. So for the double slit, the bright spots are whole numbers. The dark spots end up being half numbers. Lambda is the wavelength. Where did I use 100 centimeters in the formula? I did not. It's not relevant here because I didn't ask for anything that needed to use it. So the length comes into play when you need to relate it to the distance along the screen y. It was never used in the problem. I never asked for it. So in this case, all you need to do is just use a formula that will solve for the angle, which already has all the information you need. So actually, you don't need that distance. However, if I ask you for what the distance y is along the viewing screen, then you would say, oh, let's use the one formula with the L in it, which has tangent of theta. It's based on this right triangle right here, which you would say the tangent of theta is y, which is the distance along the screen, over L, the adjacent side, which is the distance to the viewing screen. So in this case, we don't end up using it at all. Interesting. Neither left nor right Twix. It's all Twix or it's middle. All right. So let's take a look at number 3. Ooh, there's 20 of us. Awesome. Glad you're all joining in. Number 3. This one actually took a while for me to actually design. I tried to do more with this and ended up having to cut it out. But so if you like lasers, this is a little bit about lasers. Argon lasers argon lasers use excited ionized gas. This is how I guess you would abbreviate it in chemistry. To produce a focused beam of intense light that are used in a variety of applications, including medical treatments and spectroscopy. The different wavelengths emitted by the excited gas are separated through a diffraction grading, so this might hint to you what you're supposed to do with the problem. Having 20 slits per centimeter, yes, I did use the next year to make that number up. They are displayed on a viewing screen 100 centimeters away from the grading. Measurements along the viewing screen from the center are made in centimeters. So you can see here in the figure that these two measurements here correspond to the distances in centimeters from the center bright spot. Now, I'm asking, what is the range of wavelengths that are visible on the screen? So, given that this is my picture, so here's all the wavelengths that I see on the screen. Here's the range. I have this more violet looking one, assuming that it is color accurate. I have this more violet looking wavelength, which is based on a position of 9.18 centimeters from the center. And I have this more green looking one, which is 10.7 centimeters from the center. when you get your answers, you should expect something around the 400s for the violet and something around the 500s for the green. Now, how do we calculate this range? Well, it's really just asking you to calculate the same thing twice, ultimately, because you're calculating the wavelengths of a lower and upper bound based on these two positions. Now, that doesn't actually mean you need to repeat the same calculation twice. There is a shortcut that I'll show you. In other words, you only need to calculate one of these, and you can then just multiply in a certain factor to get to the next one. So let's sort this information out. And then you're asking, so y would be the distance between the spots? No, y is always the distance from the center. Always, 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 always. Y is always measured from the center, which if it's this problem, here's the center, where this bright fringe in the middle is. It's the distance from here to whichever point on here you want to look at. So for instance, this violet line is 9.18 from the center. So again, everything is measured from the center. Unless you're doing something else otherwise, but the formulas will measure it from the center. That includes the angle. There's things you can do in problems such as find the distance between bright spots, which actually is delta y. It's not y. You would have two y values to do two different places. So like you can have a y value from the center to the violet line. You can have a y value from the center to the green line. But then if you take the difference between the two y values, you'll get like a delta y. But that itself is not the y in the equation. Hopefully that makes it a little bit more clear. So in this one, it's a diffraction grading, so you're going to end up doing something with the extra piece of information that you have with a diffraction grading. So for this one, oh, I didn't change that. Last one was 2, this one's 3. For the diffraction grading. So in this problem, I give you that the diffraction grading has 2,020 slits per centimeter. So 20 slits per centimeter. Okay. So remember that you can take the number of slits per centimeter, and all you need to do is flip it to get the amount of distance between the slits. So let me write out a short instruction here. So flip value to get the distance between slits, and that distance is d. Okay, it's the same thing as in your double slit equation. So this implies 1 over 2020 slits per centimeter. So you take 1 over the entire value, flips the units as well. So what you end up getting for this, 1 over 2020 is, in scientific notation, 4.95 times 10 to the minus 4th, and the units flip too, centimeters per slit, which you can pretty much just ignore slit as a unit. It's that many centimeters between the slits. Put it in meters, of course. So when you put it in meters, it's 4.95 times 10 to the minus 6th meters, or in other words, 4.95 micrometers. So we finally got the distance d between the slits on the diffraction grading, and we're just going to take the same equation from the double slit problem. So from the double slit problem, so solve like a double slit. So d sine theta equals m lambda. So given this value for D, so we have D, we have the, well actually we don't have the wavelengths, we're looking for the wavelengths because I'm asking for the wavelength range. We're going to solve for lambda ultimately. That means we need to know something about theta, which I don't tell you directly, but you know that you can relate that to the distance y and the distance L in the setup. So I could apply the small angle approximation. And sine of theta is approximately tangent theta, which is equal to y over L, where y is the distance from the center, and L is the distance between the diffraction grating, or where the slits are, and the viewing screen, directly to the center. So that means if we replace sine of theta with y over L, we get, this implies d times y over L, will substitute in place of sine theta, and that's approximately equal to m lambda. So now we solve for lambda because that's what we want in the problem. So therefore lambda is going to be d times y over m times L, looks like. So we plug in all the values to get our lambda. So now we pick a y value that's given in the problem. So in other words, in here, you can see that you have two y values that you can use. You can use 9.18 or you can use 10.70. I'm personally going to start with the lower number first. So 9.18, let's try that one. Now, if this is all an accurate picture, and this is, you see that this is the first set of bright spots from the center, or in this case, if I focus on the violet fringe here, it is the first violet fringe from the center, so it's m equals 1. So we'll use m equals 1 for this whole problem, and we'll use 9.18 for our y value in centimeters. So the lambda for the, let's call it violet, looks violet-ish, is going to be d, which is 4.95, 10 to the minus 6th meters, times the distance y, which we said we were going to use 9.18. So 9.18 times 10 to the minus 2 meters, because it's centi. And we'll divide by the m value, which is the first one, so we have 1. And the L, which is the distance to the viewing screen, in meters, which I said was 100 centimeters. So that's 1 meter also. So the numbers make it relatively easy. We calculate this out. So we have that number times 9.18, 10 to the minus 2. Okay. And we get our first wavelength. So the first wavelength that we get, I'm going to write it in nanometers. Let's erase this part here. So violet-ish is going to be 454 nanometers. So that's one of our answers, which means that as long as you do this correctly, you can already rule out some answers. So for instance, here, it has to be one of these first two, A or B, because it's 455, which is pretty much our answer, 454. So it can't be the other two. So now the question is it going to be 555 or 529? And we can do that very quickly, actually, by changing it by a factor. So you can either change the not the wavelength, but change the distance y and just recalculate the whole thing. It's not really a big deal. The other option is you can take this number that you got and scale it up by some amount. In other words, notice that with everything else being constant, the only thing you're changing is the value of y. You're changing it to 10.7. All you're doing is dividing off the 9.18 and scaling it back up by 10.7. So you could basically just do times 10.7 and divide off what you had originally, which was 9.18, and that will upscale it to the correct wavelength. So it's basically exploiting a proportionality. Otherwise, just recalculate it if you're not comfortable. You get for that the wavelength approximately is, for the green one, is 529, rounds to about 530 if you're going to take the number you get in the calculator, which is close enough to the answer. So our wavelength range shown in the figure ranges from 454, or in our case, in the answer 455, to 530, which is, in our answer, it's about 529. Okay, so the answer for this one is going to be A, 455 to 529 nanometers. In case you end up asking why, oh, I read the questions, and I was literally about to say that. So why is the M still equal to 1? So why do I not count all of these bright fringes in here? Well, but the thing is that, okay, so when you have a diffraction or some sort of interference pattern, like these problems that we've been doing, where it's bright, dark, and bright and dark, that is always a pattern that we analyze for monochromatic light, one wavelength at a time. In other words, in this diagram, we don't have a monochromatic setup. Now, I guess you have a bunch of monochromatics in here. You have like 9 different wavelengths, right? And they're individually monochromatic. However, if I were to focus on one at a time, so let's say I focus on the violet, the very first one. Okay, so we have this violet-ish line. If I were to let the pattern continue, this violet line would repeat further out, somewhere out here. And then it will repeat again and again and again and again. So this would be violet M equals 1, violet M equals 2, violet M equals 3, etc., etc., etc. So you alternate between dark, bright violet, dark, bright violet, dark, bright violet. So each of these individual colors are basically the M equals 1 for their own monochromatic patterns, ignoring every other color. So you have to remember that whatever you're doing is monochromatic when you use the equation. So especially if you were to have a whole gradient of color, you know, ranging from violet to red, you would have basically any wavelength you want in that range. So how would you then assign M values to anything in between there? So long story short, these are all M equals 1, and the pattern will repeat somewhere else, and there will be an M equals 2, which just repeats all the colors again, M equals 3, etc. So ignore all the other colors, focus on one color at a time. Any other questions on the diffraction grading? Okay, so the answer for this one is A. Let's go to the next one. This one's a single slit. You have a single slit that's illuminated with monochromatic 833 nanometer light, producing a pattern on a wall which is 1.5 meters away from the slit. The angular width, in other words, how wide it is in angle, of the central bright spot is measured to be 3.82 degrees. What is the width of the slit? So use the single slit equation. Okay, so our single slit equation for problem 4 is W sine theta equals m lambda. And remember that in the single slit equation, this is used to count the dark spots as whole numbers. So for dark only in this equation, and m equals 1, 2, 3, etc. Okay, so first dark spot, m equals 1, second dark spot, m equals 2, etc. Now, from here, using this equation, I need to solve for the width of the slit W, so I will solve for W. Now, I do have information about the angle in this problem. I tell you that the angular width is given in the problem. So on my setup here, with your single slit here, and the viewing screen, I'm only going to focus toward the center here. So you have the central bright spot, which is wider on a single slit pattern. So there's a very wide bright spot in the center, followed by some smaller bright spots off to the side. Okay, so I'll focus on that. I'm given the information about the central bright fringe, or what's called the central maximum. The angular width has to do with the angle you would normally use in the problem, because here's the line of symmetry down the middle. The angle is always with respect to the center. So if you take theta in this equation, so here's theta in that equation, theta is always from the center to whatever point you are interested on the viewing screen. But remember, when you're talking about the bright fringes on this pattern, they're defined by where the dark fringes are. So how wide the central bright fringe is defined by where the dark fringes are. So it's really a dark fringe question. This is the m equals 1 dark fringe, and the m equals 1 dark fringe on the opposite side. The viewing angle from the center to any of those dark fringes, so let's say this one here, the angle is formed in between here, that's theta, and that's again the theta you use in the equation. From here, this angle theta is not what I'm giving you in the problem, because what I'm actually giving you is the angular width all the way across. So the width in total across the entire bright fringe in the center, this angle from here to there, that ends up being 3.82 degrees. Okay. So, because it's symmetrical, the angle theta measured from the center is just half of it. So this implies that theta equals 3.82 degrees divided by 2, which means that theta is 91 degrees, looks like. So I'm going to use theta as 1.91 degrees, and I'll plug it back into this equation where I'm going to solve for W. So W, the width of the slit, is m lambda divided by sine theta. Okay. Notice yet again in this problem, I don't actually care about the length L, which is 1.5 meters in our case, because it's only used to link it to the distance y, which I actually do not ask for and I do not give you. So if that's the case, I don't even need to use L. I could just use the angle. So W is going to be to the first dark spot surrounding the central bright fringe. The wavelength is given to be 833, 10 to the minus 9th meters, divided by sine of the angle we just found that we cut in half, so it became 1.91, and W equals, so the sine of 1.91 is in the bottom, and then on top we have 833, 10 to the minus 9th, and that's it. So the width that I get in micrometers rounds to 25 micrometers. So the answer for this one is B. The most confusing part of this problem, or the hardest to understand, will be everything having to do with the angle. So especially let me know if you have any questions that relate to the angle. Remember that the M value has nothing to do with the bright spot. The M value in a single slit has to do with the dark fringes. So the dark fringe is M equals 1. Now, remember you don't... So with your double slit, you would be counting the bright fringes. And when you're counting the bright fringes on the double slit pattern, then you would have whole numbers for the bright ones and then the half numbers in between. So I could see that. Now, for this one, though, you are saying that the first dark spot is going to be a whole number in a single slit. So M equals 1 for the first dark spot. Now, for this first dark spot, if that's M equals 1, you're going to be using that with this line of sight that makes up the 3.82 degree angle, no matter what. So that is going to be M equals 1 no matter what you do. You are aimed at the M equals 1 dark spot. And because you are taking the angle with respect to the center, so again, remember that every measurement we use in the equation is with respect to the center. 3.82 is double the angle from the center. So you have to cut that in half to get the 1.81. Now, even if you could argue that you would be taking half the M value, so you need to use M equals 1 for that dark spot, and you would use half the angle that correlates to the angle from the center to that dark spot. Remember that when you're solving this problem, you have to solve it as if I were to ask you about the dark fringe. Are there any other questions related to the single slit? Maybe that. Hopefully, that's a little bit clearer why you cut the angle in half and not the M value. Still a little bit confused about how I got the answer. So what's the most confusing part that made it not make any sense? You calculate yourself. You're solving for the wavelength. If you calculated out 833 10 to the minus 7th, or 8.33 times 10 to the minus 7th, you calculated the wavelength. We're not solving for the wavelength. Actually, on version A, we solve for the wavelength. So you might be actually doing version A, maybe. Because I definitely ask you for that on version A. Yeah, try just double checking what you plugged in. Solve for W, plug it all in. You're plugging in the wavelength as 833 times 10 to the minus 9th. And then divide by sine of 1.91. So that's about it. So if it's single slit, we always find the dark spot. Yes. If I ask you anything about any of the bright spots in the problem, use the surrounding dark spots around the bright spot you're questioning. So if I'm asking you about the center bright fringe, on this diagram, let's say if I ask you about the center bright fringe, use the surrounding two dark spots. If I ask you about, let's say, this second bright fringe away from the center, then that means you use the surrounding two dark spots around that bright fringe to solve whatever you're looking for. Because when you use the equation, it's only valid for the dark spots. So you need to figure out what you would need to do with the dark spots to get your bright spot answer. The only other thing I can think of for why you're not getting the answer is, if you're plugging in exactly what I have on the whiteboard here. So if you're plugging in exactly what I have here, make sure you're using the proper power of 10, but it's 833 times 10 to the minus 9th because it's 833 nano, which is 10 to the minus 9th. And plug in sine of 1.91. But the other thing that can happen without your knowing is that sometimes your calculator gets left in radians and you're plugging in sine in radians by accident. So make sure your calculator's in degrees and then plug in 1.91 in degrees. That's about the only thing I can think of otherwise. So you can also use m equal to half and nope. End the sentence right there. You cannot use m equals a half on that. Well, actually, okay, I see what you're saying. You use m equals a half and you use the whole angle. Yes, it gets you the right answer, but not for the right reason. So it'll get you the right answer for the wrong reason. Oh, cool. I was like, you couldn't. There was no other way that the answer could be wrong if you're plugging in the same thing. So it had to be degrees. So glad that worked out. Just kidding. I just saw that. All right. Okay. Suppose that monochromatic light illuminates a single slit and the width of the central maximum is measured to be 10 centimeters. So this is another one having to do with the central maximum. If the wavelength is doubled and the width of the slit is decreased to half of its original size, how wide will the central maximum be? This is a proportionality question. You need to figure out what happens when you double something and when you halve something. So we're just going to recycle the same equation. We'll use the same equation. Are we going to manipulate it the same way? Not quite. Let's change the manipulation a little bit. So single slit, but now I'm telling you that the width of the central maximum is 10 centimeters. So it has to do with the y value, but 10 centimeters is not the y value itself. The y value is 5 centimeters in our problem because it's half of the entire width for the center. Because remember, the center bright fringe is symmetrical about either side, and you have to take it in half to get the distance from the center. So the y value is 5, but we're not really going to focus on that in this problem. But we know that we need to use the information relating to y. So from this equation, we need to apply the small angle approximation to include the information about y. So what we're going to end up putting in is w times small angle approximation ends up being y over L in place of sine theta. And that's approximately equal to n lambda. Now, I want to investigate what happens to the width of the central bright fringe as you change some factors. So I need to solve for a variable which is most closely related to the width of the central maximum, which is the variable y. So y is approximately m lambda L over w when you solve it. So now that I've solved for the variable that's most closely related to the width of the central maximum, because the thing is that the width of the central maximum is just 2 times y. That's it. So as long as I investigate what happens to y, I should know what happens to the entire width. So in my case, I'm going to write the proportionality. So y is proportional to only things that change in the problem. So in my problem, the m value does not change because the width of the central maximum is determined by the m equals 1 dark spot, and that stays constant no matter what. So m is not factored in. Lambda, we are changing the wavelength in this problem, so I will write lambda. The distance L to the viewing screen does not change in here, but the width W of the slit also changes in the problem, so I will write W. So y is proportional to lambda over W. you only plug in the factor by which you're changing it by. So in other words, in this problem, you are doubling the wavelength. So you plug in a factor of 2 for the wavelength. And you are cutting in half the width of the slit. So you plug in a half into the bottom. If you are careful with this, you will realize that the 1/2 doesn't cancel out the 2. Cutting in half the width of the slit actually doubles the answer. So it flips up and it becomes 4. Okay. So what this means is, therefore, how you read this is the y value after is 4 times the y value before. So the width of the entire central maximum, which is most related to the value of y, ends up quadrupling in this case. So if width of central maximum, which is 2y, okay, 2 times the value of y, since y is only half of it because it's from the center. If the width of the central maximum is 2y, is 10 centimeters before, it will be 40 centimeters after. Okay. So the answer is 40 centimeters, which is D. Let me know if you have any questions on proportionalities and how I arrived at my answer using a proportionality. So you said would equal half of WY. So in the problem, I tell you that here. So the width of the slit is decreased to half of its original size. So I'm saying that the width W of the slit is being cut in half. So when you do this, you end up plugging a half into here for W in the proportionality. So you just show that you cut in half just based on the problem. Not sure if you had something more specifically about it or if that was it. So. Okay, cool. Let's take a look at the next one then. So we have number 6 here. 2 green plants with an overall color corresponding to an approximate wavelength of 550 nanometers are some distance away from a person whose pupil is about 4 millimeters in diameter during the day. If the minimum distance between the 2 objects must be separated to just barely be resolved by the eye, as 2 separate objects is 0.168 meters, then what is the minimum distance when the pupil dilates to 8 millimeters when it's dark outside? I looked up the numbers for this too. The pupil from the eye can actually open up to about 8 millimeters, I believe. So effectively what I'm telling you in the problem is that the opening of the pupil from 4 millimeters to 8 millimeters is essentially just saying that the single opening or the single slit doubles in width. That's all it is. Doubles in width or doubles in diameter. So you need to simply write out what the resolution equation ends up being. So for the minimum distance of separation, we're going to say that for resolution. We will resort to using, we write it as capital D, but this is essentially the same as the width of the slit, W. Sine of theta, still the viewing angle, is equal to 1.22 times lambda for the resolution. The angle theta is the minimum angle at which the two objects must be separated in angle for them to be seen as two separate objects. In my problem, I am concerned with the distance that the objects are actually physically separated linearly in meters. So this is kind of like a single slit problem in a way, because it is a single opening. And you know that the small angle approximation can apply here, where we can say, again, that sine of theta ends up getting replaced with y over L. Okay? Y is the distance that will separate the two objects in a resolution problem, as opposed to a viewing screen with a distance along the viewing screen. So y is the distance between objects, and L is the distance from the opening, which is basically the slit, to the objects. Okay. So that's what you're going to define it as in the resolution problem. And then this means that D times the small angle approximation, y over L, equals, or is approximately equal to, 1.22 lambda. We need to solve it for the thing that we're investigating in the problem that we want to know more about, which is the distance that separates the objects. So what is the minimum distance that the two objects needs to be separated after we change the diameter of the pupil? So we solve for y. So therefore, y is approximately equal to 1.22 lambda times L over capital D, which is the diameter of the pupil in this case. We have the equation, and we're going to rewrite it as a proportionality because we only want to investigate factors that we're changing things by. So we have that the proportion says the following: y is proportional to, only factors that change in this problem are actually the diameter of the pupil. You're only changing the diameter of the pupil and nothing else. So the diameter of the pupil remains, but everything else is constant. The distance to the objects is constant. The wavelength of light is constant. So it's only proportional to 1 over the diameter of the pupil. Now, from here, plug in the factor that it changes by. You are doubling the diameter of the pupil from 4 to 8 millimeters. So it's a factor of 2 that you plug into the bottom, which means that you get an overall number of a half because it's in the bottom. So doubling something in the denominator will give you a value of a half in this case. So this therefore says that the y value after is equal to 1/2 of what it was before. So y after is equal to 1/2 of, now I said before it was 0.168 meters. And we just take half of that, so the final y value that they must be separated by at minimum to resolve them when your pupil is dilated is going to be 0.084 meters when you cut that in half. And that's one of your answers. That's answer C. Let's see if we have any questions on that. So resolution is like a single slit? Yes, because the opening in the eye, the pupil, is just literally a single hole. So it behaves like a single slit, basically. And your equation looks very similar to that of a single slit, where the diameter of the opening, capital D, is basically just the equivalent of the width of the slit, W. So you can draw a lot of analogies between the two problems. Could you solve for y using the distance 0.160 meters and the pupil at 4 millimeters, and then use that value of y in the equation with 8 millimeters to solve for d? You're not solving for d, you are solving for y. What you mean is, at the very end of what you said, use the value of d rather in the equation to then solve for the value of y. So basically what you said is correct. There is one detail that you are actually going to need to solve for in the problem that's missing, is I never told you the distance from the person to the objects. So if you want to calculate out values, you need to calculate the distance to the person first. And then you can basically follow through with what you said to solve for the distance y between them after the pupil is dilated to 8 millimeters. But that's the long way. So you can do that if it makes you more comfortable with it. But if you find yourself in a time crunch, do it the way that I did it, which is significantly faster. Especially if you do things like you take the MCAT or things like that, they'd like to ask you these kinds of questions. So you have to learn how to use proportions. But otherwise, the answer is yes, you could do that. If you actually calculate out, would y be equal to 0.084? Yes. When you calculate it out is doing the same thing that I'm doing. I'm just basically exploiting proportionalities to say that it will either upscale or downscale by a certain factor. So in our case, doubling the diameter of the pupil will just simply cut your value of y in half. That's it. So you can either calculate it out or you can use proportions. It doesn't really matter. You'll get the same answer. Okay, so for number 7, this one is a layer of oil, which I actually gave the index of refraction for this time, but I'm using a different index of refraction. If you did watch the first live stream or you did the first version of the practice exam, which I think I forgot to put into there when I revised it, I used a lower value for the index of refraction on the first practice test. I think it was around 1.2 something. So in this problem, we are using 1.5. Beyond that, so for this problem, you have the index of refraction for the layer of oil, which sits on top of a layer of water, which also has the index of refraction given. That should be somewhat familiar. It's exposed to the atmosphere, meaning that there is air on top of the whole system, followed by the oil layer, and then followed by the water underneath. What is the minimum thickness for the oil, minimum thickness of the oil for 700 or 475 nanometers to be observed? So we need to do what's called a thin film problem, and we're going to set up the equation for that. And before I jump into that, what would L be for problem 6? L is the distance to the objects from the person. It's basically the distance between the opening or the slit and where the objects are. So for this one, the thin film interference, I'm going to write the equation out. I'm going to emphasize it a little bit simply, at least because it's not correct on the formula sheet and it's going to be corrected on the actual exam. But the thin film interference has the following equation. We'll write it this way on the formula sheet. It has 2nt divided by lambda plus capital Phi equals, and the correct version of this formula is just equal to m. There is no lambda on the other side of the equation. Personally, I prefer to have the lambda not in the denominator. So in other words, I would have personally written it as 2nt plus this factor times lambda equal to m lambda. Okay. This is just rearranged. It's the same thing. Now, so given that you have this equation, so what do each of the things mean? Okay, so let's go over conceptually how this is used. So n is the index of refraction of the film. Index of refraction for the thin film. T is the thickness of your film. In this case, it's the oil. Lambda is the wavelength, so it's just as usual. This factor here is the relative phase difference. Okay, relative phase difference. I'm going to go a little bit over how we're going to do that to solve the problem. And m is the order number, as usual. Okay. This is pertaining to your bright and dark spots, basically. Count the spots. Now, for this problem, you have your thin film. Okay, so here's the oil. And the index of refraction is 1.5. This is compared to the air above, which has 1.00, and the water underneath, which is 1.33. Okay, so now, in the thin film problem, here's the basic summary of what happens. You take light. Let's use this color here. So the light comes in, hits the first surface, and we know two things happen at any surface is it reflects and it refracts. So we get a reflection off of that, and some of it goes into the oil. It refracts inward, it bends in towards the normal. It's going to hit the second surface, and it's going to do also two things again, reflect and refract. We're not going to care about the part that refracts, which just goes out this way. We're going to care more about what reflects off of that surface and then pops out, refracts out. Okay. You could technically get another reflection off of that, but we're not going to concern about that. We care about these two rays of light that pop out. Now, this is where we are going to talk about the relative phase difference. Okay. How do you get this factor? Okay. It's either going to be 0 or a half in your problems. So here's how you get 0 or a half without flipping a coin. You have to remember one conceptual detail is that when you go from the low index to a higher index, there will be a phase shift in the light. So you have, for example, you have these waves here. So light is a wave, here's the wave. And there's another wave here, and they're lined up. Okay. These two waves would line up, creating constructive interference, and you would see a bright spot somewhere. Now, let's say that we have a phase shift. So a phase shift means that the wave is shifted by some amount. Now, this 0 or a half, or whatever value we end up using, has to do with how much of a wavelength. So is it shifted by 0 wavelength, or is it shifted by half a wavelength? So if I were to shift it by 0, then you leave it the way it is. If you shift it by half a wavelength, then moving it over by half a wavelength changes it from this to the following. Will be this. That's destructive. So remember, destructive occurs when you shift it over by half a wavelength. Now, it has to do with shifting the wave around and kind of making it constructive or destructive. Now, if you go to here and we apply the concept, which I'm saying is if you go from air to oil, this is low to high because it's 1 to 1.5. When you go from low to high, low index to higher index, you get phase shift. And it's going to be 1/2. Okay, so you'll have a phase shift of half of a wavelength. When you do the opposite, high to low, there's no phase shift. 0. This is where you're going to get the 1/2 and the 0 from, but we're not quite done yet. Let's go back to the diagram. So we go from low, being the air, to high, being the oil. Low to high means there's a phase shift of 1/2. So on the ray that reflects off of the top surface, the boundary between the two we just discussed, the reflected ray will see 1/2 of a wavelength shift. So we write 1/2. Now, the second reflection comes from going from high to low because we have 1.5 on top and it tries to go into the water, which is 1.33. So that reflection off the second surface comes out and there is no phase shift at all. So now the relative phase difference or phase shift is the difference between those two phase shifts that we have. So in other words, we have 1/2 and we have 0. Right there, the phase shift or difference is 1/2 minus 0, which is still 1/2. Okay? So that's the value we use for the phase difference or the phase shift in the formula. In some problems, the index of refraction below the film will end up being higher. So you'll go from low to high yet again, and you get a second phase shift of 1/2, and then the difference ends up being 0 instead of 1/2. So pay attention to what the order of the indices are, and say, are you going from low to high with each boundary? So low to high, in this case, high to low instead of again low to high. So now, when you actually calculate this problem out, so I'm asking you in this problem for the minimum thickness of the oil layer. So I need to solve for the thickness T first. So in this equation, I'm going to solve it for T by doing the following. I'm going to subtract over the phase difference between the two reflections to this side. So I have 2nt over lambda equal to m minus the phase difference. I'm going to multiply by lambda and divide off by 2n to isolate t. So therefore, t is m minus the phase shift. We've multiplied by lambda, so that whole thing. And we're going to divide all of it by 2n. So we've solved for the thickness, and now we just need to figure out how do we calculate this to satisfy the minimum requirement. So I'm going to erase a little bit of the stuff from here, so let me know if I've lost you at any point so far, if you have any uncertainties about what I've written so far, or any general questions, and then what I'll do is I'll erase some of the left side to solve the rest of the problem. if that last question was pertaining to the thin film interference that we're doing now, if it's constructive or destructive, the problem is either going to say something that indicates that, such as bright or dark, or they'll explicitly state it. What we're going to find in our case is that now, I guess when you look at the wording of this, if you are observing light, then it's a bright spot. It's going to be assumed that when you do these problems that you're looking at either the middle of a bright spot or the middle of a dark spot. Because you're looking at a wavelength, you are observing light. That means you are using a bright spot in this problem. Hopefully that answers that part there. What would the M value be in this problem? That's what I'm about to go into, because I didn't indicate anything in the text that would tell you explicitly, oh, I need to plug in this number or this number. There is one word only that actually indicates what you're supposed to do with the M value, which I'll show you in a second. Okay, let's erase the left half of this. So I'll erase some of it. Okay, so here's what I'm going to plug into the thickness. In the wording of the problem, I said that I want the minimum thickness. In other words, you need to give me the smallest value of t that's possible. Now, the equation is going to tell you all the possible values for the thickness for whatever value of m that you choose to put in it. Because given that the index of refraction of the oil is a constant, which it is, it's 1.5, that plugs into the bottom, we're not changing that. Given that the wavelength is fixed for the problem, which it is, we're not changing that either. I gave it to you as 475 nanometers. And given the phase difference is also a constant, which it is because it depends on the setup. So the setup's not changing, so the phase difference stays constant. The only thing that you're allowed to change in this problem, given the same setup, is the value for m. So for every value of m, which is going to be a whole number, 0, 1, 2, 3, 4, etc., you will get a different value for the thickness that is required to see that particular m value. Now, the thing is, though, is I'm specifically asking you for the smallest value of t that is possible in this equation, the minimum amount. That means you must choose the minimum m value that is possible that would satisfy this equation. Now, if you look at this, though, the phase difference is 1/2 that we determined earlier. So you have to take whatever value of m you're using and subtract off 1/2. Which means that you cannot use 0 for the m value. Using 0 for the m value, subtracting off 1/2 gives you a negative number for the thickness, which is not possible. So that means the smallest value of m that's possible for this equation is 1. So minimum thickness implies minimum m value. So if thickness, if t depends on m minus the phase difference, where the phase difference is 1/2, then m minimum can be 1. Okay? Whole numbers. So I get that m minimum must be 1 in the equation to give me the smallest thickness possible. So now, again, because I don't really care about the details of the different bright and dark spots that I would observe in the film, since I don't care about any other details about those bright and dark fringes, and I only just care about the minimum requirement, I just plug in what numerically gives me the minimum value. So in this case, we have that the thickness is 1 minus 1/2, which gives you 1/2, the smallest possible positive number in there. times the wavelength of 475 10 to the minus 9th meters divided by, and then we have 2 times the index of refraction for the oil, 1.5. Okay. So plug this all in for the thickness, and I believe I remember doing this earlier. You get 79 nanometers for this calculation. Let me know if you get the same thing, but I believe it's 79. And 79 corresponds to answer D. So we wouldn't use the equation that has m plus a half. Yeah, whatever the other equation, whatever the other form of the equation is for destructive, you do not use it because you were observing a bright spot. You were observing 475 nanometers for the light, so it's bright spot. How do we know to use 2.5 and not 1. You mean 1.5 and not 1.33? Because the index of refraction is for the film. The film is what sits between 2 different layers. Also, the definition in and of itself is for the film. You could technically have a film of water. You could technically have water sandwiched between 2 different other materials, but in this case it's oil between 2 different layers of air and water in this case. So the film is oil. I thought we were using a difference of 0, not a half. Well, okay, so no, the phase difference is the relative phase difference. Look at path 1 and the reflection off of surface 1, and look at path 2 and the reflection off of surface 2. Get both of the phase shifts. You get 1/2 for the top reflection, 0 for the bottom reflection, and you take the difference between them. So you take a half and subtract off 0, and the answer is a half. So you're using a half for the phase difference in this case. Okay. Everybody good? All right. Let's take a look at the next one. Okay. We have we have 3 relativity questions in here, which encompass 3 of the main topics in my opinion. This one's a repeat question from the last practice exam that I didn't change. This one's a quick one, just application of photoelectric effect. And then we're going to eventually get over to the last stretch, which is hydrogen atom, and then the other chemistry topics that we would talk about. So for number 8, we're going to consider someone standing on the ground that watches another person riding a super awesome skateboard, which is capable of traveling with a speed of 0.5 c or half the speed of light. The skateboard rider launches a projectile with the speed of 0.7 c in the direction opposite to their motion. Relative to the person standing on the ground nearby, how fast would the projectile appear to move at? So you have 2 different points of view. You have the point of view of the person on the skateboard, and you have the point of view of the person standing off to the side. So this one, you have 2 different velocities that get combined. This is analogous to you being at an airport. You go on the little conveyor belt to make your journey through the airport faster. You walk along the conveyor belt. So what happens is you add your velocity to the velocity of the conveyor belt, and you move faster relative to the ground. So it gets you somewhere faster. Equally, you could run in the opposite direction on the conveyor belt, like you would do if you were 7 years old or perhaps if you're just messing around with some friends or something. But if you run in the opposite direction, it just slows you down. So now in this problem, it's pretty much analogous to that. Is you take the speed of the skateboard, which is 0.5 c, and you're going to either throw something with or against the direction of that motion. But in this case, you're throwing it in the direction opposite to the motion. So which means you should expect that something gets subtracted, not added. So let's write out the equation that we use for this, which is the relativistic addition of velocities. Relativistic is always a term that's used when you are dealing with things that are moving closer to the speed of light. So now, the relativistic addition of velocities is, for problem 8, velocities. Okay, so we have u equals u prime plus v divided by 1 plus u prime v over c squared. So I'm going to take this equation, and this is the special way that we add velocities to each other when things approach the speed of light. So u prime is defined as the velocity of, in our case we're using a projectile, we'll just say projectile, in point of view of person on or in moving frame of reference. Let me boil this down a little bit. Here, let me draw the drawing here so you have a visual of what I'm trying to describe here. So there's a person on the skateboard. Okay, here's the skateboard. And here's the person on the skateboard. They have an object that they're gonna throw. Now, if you wanted to, I guess, let's say we just draw an imaginary box around this skateboard. Okay, so this person is attached to the skateboard, and this whole box that I've drawn here that surrounds the person in the skateboard, this whole box is moving to the right with a speed of 0.5 c. So that velocity there is actually the velocity v in the equation. The velocity that the object gets thrown at with respect to this person is u prime. That equals, well, here you have to be careful because velocity counts for direction. We have to account for the direction, so it's either plus or minus. So if we take plus to be the direction of motion, they're throwing it backwards, so it's minus 0.7 c. This is the velocity as measured by the person on the moving skateboard that's moving with respect to the ground. The person on the side, standing on the ground, not moving with this, sees this object being thrown, and they see, so when you ask them what velocity they measure u. Okay. So they're not going to see this object being thrown with 0.7 c. They're going to see it thrown with a different velocity because it gets added in a special way to this one. So in this equation here, u is velocity with our velocity in point of view of person with respect to ground. It's the person that you're treating as stationary. So quote unquote stationary. observer. Okay. And then v is the velocity of the moving frame. These are the more precise definitions, but perhaps looking at this picture will help you to interpret what those are specifically. So, long story short, u prime and u are basically the velocity of that thing, but measured with respect to someone's point of view. Is it measured with respect to the person's point of view on the moving platform, or is it measured with respect to the point of view of someone who's treated as stationary on the side? So you just plug in all the numbers into this once you realize what it is. So u equals u prime, which is minus 0.7c, plus the velocity of the moving reference frame, which is 0.5c, divided by 1 plus, multiplying the two numbers together, so negative 0.7c times 0.5c divided by c squared. So plug in all of those numbers. Essentially what's going to happen is these c's in the bottom will cancel with c squared there, so you can pretty much ignore the c's in the bottom. In the top you collect the c's out, and the answer will be in terms of c. So given that you realize that, you can just practically ignore all of the c's and just put a c in front of your answer. In this case, in the top we get 0.5 minus 0.7 is minus 0.2 divided by the bottom. When you calculate this out, it ends up being 1 minus whatever that is. So 1 minus 0.7 times 0.5, and you get 0.65. And that ends up being positive because 1 minus that doesn't end up being negative. And then u finally is times negative 0.2. And your answer is negative 0.31c. So in other words, the person standing off to the side, stationary, that you're treating them as stationary with respect to the ground, they see this object being thrown backwards, not as 0.7c, but as actually 0.31c. And the negative indicates that it's going backwards, not forwards. So this is only to do with the direction. So the speed is just the magnitude of this, which is just 0.31. But if you need to care about the direction, the minus means backwards or to the left. Let me know if you have any questions about how this equation is applied, and then we'll quickly do the other two relativity problems. Good so far? Okay. So the answer for this is A, 0.31c. Now for these. Okay, number 9 is a time dilation problem. Now, I can briefly do this one out. However, I didn't really change much about this. It's really pretty much asking the same thing as the other one, but just worded differently. The answer ends up being the same as the last practice exam version, which was 30.2 years. So I'm going to quickly write out what you would do to solve this, but I'm not going to go into as much detail since I did it on the first one. So rewatch it on the first live stream for how it's basically done, but I'll show here briefly. So in this problem, you have Earth, spaceship, and there in this problem I say that the astronaut, which is on the spaceship, leaves Earth and they come back to Earth, and it takes 20 years to complete according to an observer on Earth reading their clock. So person on Earth has a clock and they say it's 20 years on their clock. Okay. And there's a clock on the spaceship. Okay. And the person on Earth sees their clock as stationary, but sees the spaceship's clock as moving. So, according to time dilation, delta t equals delta t naught over square root 1 minus, or actually I'll write it this way. The more compact way is gamma times delta t naught, where gamma is defined as 1 over the square root of 1 minus v over c squared. Okay. So this basically says that delta t naught is called the rest time, which I actually realized it's synonymously called the proper time. I had actually previously thought it was the proper time is the other one. The proper time is the rest time. So delta t naught, the rest time, is the time measured for a clock that appears to be at rest. Delta t is the time measured for a clock that appears to be moving. So, in short, this is a clock that's moving, so a moving clock. Okay. The key point is that the clock has to look like it's moving. So the person on Earth sees the clock move away from them on the spaceship there. So this one appears to move with a velocity of 0.75 c to the right in this picture. Now, of course, there is an astronaut on the spaceship, but when they look at their own clock, they don't see their clock moving. They see their own clock as stationary. So you have to always pay attention to which clock you're looking at and from which observer. So, person on Earth sees their clock moving, so that's the moving clock time. This one is the rest time, so it's the clock at rest. Okay. So in this case, the clock at rest is 20 years. So the clock that the person on Earth sees on the spaceship is dilated, which is delta t. So you plug it in, you calculate this all out, so it's 20 years divided by this factor, 0.75 c over c. Cancel it out, you'll get 30 years approximately. Okay. And the answer for that ends up being C. So I guess this is a very slightly different explanation of what I did in the previous live stream. So go rewatch that for a little bit more in-depth. But this is more or less the summary of what that is. The next problem has a similarity to the first practice exam, but it is a different problem. I did modify something significant to it. So in number 10, this is a length contraction problem. The length and the height of a spaceship moving at 0.5 c, as observed by an observer on Earth, are 100 meters and 10 meters respectively. So in other words, the length of the ship is 100 and the height of the ship is 10 meters. What is the length and the height of the spaceship as measured by the astronaut in the spaceship? So, remember one key concept here is that in length contraction, lengths in the direction or along the direction of motion are the ones that are contracted when you see the length moving. The lengths that are perpendicular to the direction of motion are not contracted. So immediately, if you realize that the height of the spaceship is perpendicular to the direction of motion, so the height is 10 meters, that remains unchanged because it's perpendicular to the direction of motion. So the only possible answers are actually only A and, oh, I didn't change those. Whoops. That would be E and F on here. So the only possible answers are A and E. Now, you can actually already narrow down the answer without actually doing the problem, because this first answer, A, has that the lengths are unchanged. That cannot possibly be the answer. You can actually solve this entirely with process of elimination. Now, if you want to see how you do it, then this is how you do it. So briefly, applying the length contraction equation. This is also, this part is the same as the last live stream, so I will summarize that as well. So in here, for length contraction, you have that the length L is L naught divided by gamma, and the definitions are very similar. So L naught is the length that appears to be at rest, and L is the length that appears to move. Okay, so again, remember, ask what the person sees. There are two observers. You need to ask what do they see in their point of view. The person on Earth sees the length of the spaceship moving around in space. The astronaut in the space station does not see their space ship moving. They see everything else around the spaceship moving. So, depending on your perspective, that is who sees a rest length and who sees the non-rest length. So in this case, because I want to know what the astronaut sees as the length of their spaceship, they measure their spaceship as if it looks like it's at rest. They do not see their spaceship moving. So I need to solve for L naught. So L naught is gamma times L. If you had already calculated gamma, it ends up being 1.5 from the previous problem as well. It's the same speed. So plug in the numbers for gamma. Multiply that by a length of L, which is about 100 meters, and you get approximately 150 meters. It's actually about 151. Okay, so this is the length that the astronaut would measure the spaceship in their point of view. Meanwhile, the person on Earth who watches the length of the spaceship move through space, it's going to be shrunk or contracted, which will end up being 100 meters in their perspective. Those are all the relativity questions. Let me know if you have any quick questions on the relativity, and then we'll go on to the next question. Okay, so the answer for that was E. So if the length is in the direction of motion, okay, so it's either stretched or contracted depending on your point of view, but the idea of length contraction is that when you observe a length to be moving, it's contracted. In the direction of motion. So if you have a length and you have a height of the spaceship, the height is not in the direction of motion, it's not contracted. And when you see the length of the spaceship as in the direction of the motion that you see for the spaceship, that one gets contracted. So then it gets shrunk from 151 was what the astronaut sees, and then the person on Earth sees 100 for the length of the spaceship. For 11, I'm going to skip this one because it's the same as the practice exam before. So for the explanation on this, refer to the previous live stream. It's exactly the same. It's identical. The answer for this one ends up being 5800 Kelvin. And all you do is you use the black body radiation peak equation, which says that the frequency peak is a constant times the temperature. It's also known as Wien's law. So apply that and you're going to get 5800 Kelvin for that. So I want to get to the meat of the last part of this practice exam. So photoelectric effect and the remaining bits, quantum and atomic. So this one here, a spectrum of bright light with a specified frequency range based on intensity peaking at 3.41 times 10 to the 14th hertz. That range goes from that number, goes down to half of that number, and up to twice that number, the peak value. So again, there's a frequency range here where I'm saying there's the minimum value is half of this, and the maximum value is double that value. Which of the following elements with given work functions, so all of these options below are the elements and their work functions, would see electrons ejected and creating a current in a circuit? List all answers. So there's multiple answers in here that you can choose from. So that means we need to just basically figure out, is it going to eject or not? Now, I'm going to tell you right now that despite the details in the problem about a whole frequency range, I want you to realize that conceptually the only thing that matters is that in that frequency range, there's going to be one end of the range which has a lower energy, and there's another end of that range which has a higher energy. You care about the one that has the higher energy because you're trying to get the electrons ejected, which require more energy. So in order to solve this, all you really need to do is use the higher energy, and that's it. So frequency continues to increase with energy, so we're going to use the high end of the frequency range. So we're going to take double this value here to get the highest energy possible. So double the frequency and use that. Now, we don't actually need to use a full equation here because all we need to do is find the energy of that photon. So what we're going to do first is calculate the energy of the photon. So the energy of the photon is going to be E equals H times F. Okay, that's it. That's the energy of the photon. A side note, which is an important one to know, is that this E equals HF, the energy of that single photon, is part of the photoelectric effect equation. Electric effect. It says that the maximum kinetic energy, which is also written as E, by the way, but I'm going to write it as K maximum, equals HF minus the work function. And in that photoelectric effect equation, you'll see that there's an HF in there. That is the photon energy in the equation. Okay? So it is the same thing. Okay? So really, all you need to do with this is basically see if the photon energy exceeds the work function. That's it. That's what determines if it ejects or not. So I need to calculate HF. So E equals H times F equals, you have two options for Planck's constant, and I would highly advise that you plug in the Planck's constant in electron volts because it's given on the formula sheet. Straight off of that, you can plug in Planck's constant in electron volts as 4.136 10 to the minus 15th electron volts times seconds. And use Planck's constant in electron volts so that when you multiply it to the frequency that you want to use, so we're going to use the highest one in this case, I'm going to use double our given frequency, so again over here, the range goes up to twice the peak value. So I'm going to take this frequency and I'm going to double it. So doubling that will give me 6.82 times 10 to the 14th. So 6.82 times 10 to the 14th hertz, which is the same as 1 over seconds. You'll see that the seconds cancel out and it leaves you with electron volts. And the reason why I wanted Planck's constant in electron volts in the first place is because the work function is normally given in electron volts. So we want consistency. So plugging this in, we get 6.82 10 to the 14th and multiplied by Planck's constant in electron volts, 4.136 10 to the minus 15th, and we get 2.82 electron volts. That's it. This is the photon energy. So does this photon energy exceed the work function requirement to get the electrons to eject? So all we're going to look for is this number greater than or equal to the work function? So if we look at our answers here, we have these work functions. So platinum is a no, nickel, no, iron, no, sodium is 2.82. Let me make sure if that's, that might be a typo, but sodium has a lower work function. So that's a yes, apparently, according to this. So sodium and cesium. The reason why I was questioning the 2.82 is because it's coincidentally the same answer that I got. So apart from that, you have sodium and you have cesium where our photon energy exceeds that work function. So the answers are D and E. If for some reason I wrote the work function for sodium incorrectly, it still actually is sufficient. So it's still an answer. So D and E are the correct answers. Let me know if you have any questions on the photoelectric effect, and we'll do the hydrogen atom related stuff. Okay, so the hydrogen atom. Number 13, you have a hydrogen gas that's excited, yada, yada, yada. The red emission line shown below here corresponds to the smallest energy transition possible, 2 n equals 2. So that's going to be the final energy level that we end up at. What is the wavelength of this light? Okay. Now, of course, it's the red emission line. I am telling you that, so you should kind of already expect the answer is going to be around red somewhere. Even without telling you that's the red one, you can still solve this by saying that we want the smallest energy transition possible to where it ends up at n equals 2. So for this, use the Rydberg equation. So in the Rydberg equation, you use it when you want to talk about energy transitions in the different energy levels or states in an atom. At least in our case, we're only going to concern about hydrogen, but there is also a modification that you can use for anything that's not hydrogen. which is just you take the atomic number, you square it, and you multiply it in, but we're not going to care about that. So we use it for energy level transitions for electron. Okay. So we have 1 over lambda, the wavelength, equals Rydberg constant R times 1 over n prime squared minus 1 over n squared. N prime was the energy level that you are transitioning to, which is in this problem n equals 2, and n is the energy level that you start from. So I will write here a little note to summarize that, is that electron goes from energy level n to n prime. Okay. Conceptually, the electron has to go from a higher energy level to a lower energy level because it has to release energy, which is in the form of light. So when you see the light from this, it means it had to drop in energy level. So must go from high to low to release energy, which is light. And I think we're done with this marker. Okay. So when you observe light, it's releasing energy. It's going from high to low. Now, take this equation and I tell you that we're doing the lowest or the smallest possible energy transition to n equals 2. So my question is ultimately saying is what is the smallest possible transition to n equals 2, but you could say that it's n prime in our case. Okay, it's n prime because that's where we end up at. So the smallest transition is the next possible integer value, which is n equals 3. So this implies n equals 3. It's the next possible number. So now we solve for the wavelength. I'll just write the values you end up plugging in. So R is 1.097 10 to the 7th 1 over meters. Constant given on the formula sheet. These two values are given up here. And you solve for lambda. Don't forget to flip at the very end because it's 1 over lambda. And in doing that, you will arrive at lambda equals, so after plugging all your numbers in, lambda is 600 and I think it's 656 nanometers. 6.56 10 to the minus 7th is what it is. So the answer is D. Let me know if you have any questions on how that's done, and we'll do the last topic. N is greater than n prime. It is. So n is greater than n prime. So in this statement here, I'm saying that it goes from n to n prime, where in this case n is greater than n prime. So it goes high to low, high to low. So 3 to 2. And here, n prime is 2, n is 3. So it is exactly what you're saying. How do you know the given n equals 2 is n prime? That's because I said that you are going to n equals 2. It's a transition to n equals 2. You're going from n equals 3. So the keyword is actually the most subtle word. It's the word 2. So if we are investigating the maximum transition, that's when the n term would work out to be 0. Yes, the term ends up being 0, but the n value for the largest transition is infinity. You take a ginormous number for n, and it will be 1 over a ginormous number, which we just call infinity, and that's 1 over infinity being 0. So yeah, you could do the same thing for the maximum or largest possible energy transition. If I asked you that question, then the answer would end up being C instead of D. All right. And then the really short questions. And then we're done. All right. So final questions. How much energy would it take to remove an electron from the ground state? So notice the keyword from here. It starts at the ground state, which is also n equals 1. Completely. So remove it completely from the hydrogen atom. So you know that the electrons sit in these energy levels. Okay, so they're in different orbitals. When you remove it completely from the atom, you are raising its energy level, not lowering it. So this is not a hydrogen emission problem where we go from high to low. This is taking the electron in a low energy state and moving it up to a high energy state. Specifically, you're moving it up to infinity, basically. So you remove it completely from the atom. Now, in that case, you could just then say, okay, if I want to calculate energies, then what I use is the following equation. It's the energy levels in a hydrogen atom. So I have energy levels n equals 1, 2, 3, 4, all the whole numbers. And the actual amount of energy in electron volts for each of those levels. So energy in hydrogen atom levels. So E subscript n equals minus 13.6 electron volts divided by n squared. This equation will precisely calculate the amount of energy associated with that energy level. So the thing is that the ground state, which is n equal to 1, has that E1 equals minus 13.6 electron volts divided by 1 squared, which is minus 13.6 electron volts. Okay, so that's the energy associated with the ground state. Now, to remove something completely off of the atom, to take the electron fully out of the atom, you are pulling it through all the energy levels, which means you're taking it out to infinity. So remove electron. If you know your chemistry terms, this is equivalent to saying that you are ionizing the atom. So in other words, this is the this is ionizing. This implies that n goes to infinity. And in that case, E infinity is minus 13.6, which we won't end up caring about because infinity in the bottom, you put any number over a ginormous number, it's practically 0. So E infinity goes to 0. So when you compare the difference here, the difference is 13.6. So you're going from here to here, so 0 minus that. So if you do E final, which is E infinity, minus E initial, then the difference is double negative, so it's 13 13.6 electron volts. So the energy needed to ionize the atom or remove the electron completely from the atom is 13.6 electron volts. So the answer to that is B. Let me know if you have any questions on that, because I know we haven't done so much with that. All right. And we're slightly past 11, so I know this is probably a good time to wrap up too. So let's finish these. So 15, for an electron in an energy level of n equals 2, how many possible electron states can there be? So this one, I'm just giving you an n value, and I want all the possibilities for its state. This is going to go into, okay, so we're going to questions. This is going to go into using the other quantum numbers, the L, the m sub L, and the m sub S, the electron spin. So all possible states for n equals 2. Okay. So for an n value of 2, we'll have some L values, some m sub L values, and we'll have some m sub S values. Remember, the rules are going to be L can be any number up to n minus 1. So L can be, I'll space these out a little bit more. So I'm going to do 0, I'll do 1, and I'll do 2. I'm sorry, 0 and 1. We do maximum of n minus 1. So for n value of 2, the L maximum is 1. Okay. So 1 minus that. Now, for each of the L values, we will consider the following. For, let's say, an L value of 0, m sub L can range between minus L and positive L. Now, because L is 0, that means there is no range on it. Okay? Minus L to L, well, L is 0. There is no range. Now, with this, m sub S is always 2 values, period. Spin up, which is positive a half, and spin down, which is minus a half. We can shorten that as plus or minus a half, but there's 2 different combinations here. For the L value of 1, m sub L can range between negative L, which is negative 1, and positive L, which is positive 1. So we can include negative 1, I'll space it out a little bit, 0, and positive 1. Okay. So here, notice that the range is negative L to positive L. Now, on each of these values, you can have a spin up and a spin down on this. So plus a half, minus a half, plus a half, minus a half, and then plus a half, minus a half. So how many combinations there are? 1, 2, 3, 4, 5, 6, 7, 8 combinations for the n equals 2. So the answer is 8, and the answer is D. Okay. And since the last question is very similar, I'll do the last question and I'll answer any remaining questions at the end of the last question. So I'll try to do it actually in the space that we have so I can keep this up on the board. The last question is, what is the maximum Z component of the angular momentum for the 2p electron state. So, refresher on the electron state, the 2p. So this is the final one, which is 16. This one was 15. 16 has that the 2p state breaks into two pieces of information. The 2 out front is the n value, so n equals 2. And p is part of the S, P, D, and F. So remember that S, P, D, and F means that the L value is either 0, 1, 2, or 3. So in our case, we want P, so that means that L equals 1. Okay. So we're going to say that the L value is 1. Now, the Z component of angular momentum has the following equation: LZ equals L times H bar. That's lowercase l. Or m sub l, sorry, m sub l. Okay. So we just need to plug in the correct m sub l value, and that's it, because we're just gonna leave that in terms of h bar. Now, m sub l has a range, because remember from over here we said that m sub l could be anything from minus l to positive l. So what do we choose? It could be minus 1, 0, or even positive 1. If we look at all those combinations there, you could plug in any value into there, but I am telling you that I do want the maximum possible value. So the maximum is going to be 1. So if I do the maximum, which is L equal to positive 1, that means, or m sub l, sorry, keep doing that, m sub l equals positive 1, then LZ component is just 1 times h bar. That's it. And that means the answer is D. And with that, let me know if there are any last questions on the remaining topic, and we'll go from there. And then I will repeat some of the information I said earlier about what we're going to be doing tomorrow, including candy. Any more questions before we call it a night? And I hope you're no longer hangry. If you're still hangry, go feed yourself. No more questions? Okay. All right, so this is the last live stream review, I believe. I don't plan to do another live stream tomorrow morning because I'm going to use that time to probably sleep in just a little bit, but I got to design your last practice test. So tomorrow at 1 p.m. we'll go over a last version of the practice test. I'll try to mix it up as much as I can with the time that I have. And this will probably be the last live stream. So what I'm also going to try to do tonight is I'm going to try to see if I can design something that goes on my website that lets you take the practice test online with multiple choices. So you can gauge if you're right or wrong on questions before we actually go over it in person. So if I do that, I'm going to post the information on the Canvas, and you'll probably get an email for that. Otherwise, I don't think we have any more questions. So thank you for following me in the live streams. And again, if you enjoy what I've been doing with these live streams, tell your friends about what I'm doing. Tell them about all these live streams, the website that I'm building over time, and then help me to continue growing in viewership. So thanks for tuning in, and I hope you have an awesome night.